So, last class we did the flow through a pipe, round pipe for uniform heat flux. This time let us take the case of uniform wall temperature. So, this is the other extreme, and we will use the same methodology that we used earlier, but in this particular case only the wall temperature. So, if this is the pipe once again, this is the central axis. So, this wall temperature is T naught. T naught now is a constant. Obviously, your heat flux is not a constant anymore, right, because last class that is what we saw, that your heat flux is a constant, and we could apply some nice little tricks, and we could show that the Nusselt number was approximately 4.66 4.36. So, this time we will see that what the Nusselt number value will be, because that is one of the main purpose. Once again, like in the external flow, here also the main intention is to find out what will be the value of Nusselt number, okay, and we showed for that you need the temperature profile, okay. So, similar to last time, this is of course given, okay, it is 2 by R naught. This is a common thing that we wrote initially, okay. This, if you recall, is the average axial velocity, okay. Q double prime is equal to H into T naught minus Tm as a function of x, right. That was also kind of given, or in other words dTm by dx 2 by R naught H T naught minus Tm as a function of x divided by rho CPU, right, okay, or dTm by T naught minus Tm equal to 2 by R naught H by rho CPU into the corresponding dx, right, okay. So, I am just using the standard definition that here of course Q, why did I do this? Because my heat flux is no longer a constant, right, because it is not a constant heat flux problem. So, as you know, your mean temperature can only be a function of x, because you by definition the mean temperature takes into account the radial variation, because it is integrated over the radius of the pipe, right. So, it will be only a function of x. So, therefore, once you, and this is the generalized expression, the conservation of energy expression that we wrote 2 classes before. So, basically I have done just this much, right. Now, let us look at, so now once you integrate the whole thing, right, it offers you that you can integrate. So, it is basically given as okay. So, what does this mean? X1 means, X1 is basically the region of fully developed flow, that is the fully developed flow starts, right, is a fully developed limit, okay, and Tm at X1 is basically the temperature at the fully developed limit, at the starting point of the fully developed regime, right, and of course H is Nu R naught K by 2, okay. So, using these two we have got this expression, this full expression, right, okay. So, some interesting points to note about this particular expression is, let me write it once again clearly so that you guys can kind of appreciate. Where x1 is the fully developed limit, right. So, that is the expression. Now, using this expression you can see that this is the start, right, this is the maximum variation of temperature. This is the starting point of the fully developed regime, right. After that you can see that the T naught minus Tm term actually starts to go down exponentially, right. If you can look at, because it is exponential minus, right. So, T naught minus Tm, this particular expression starts to come down exponentially, right. That is what is given by this form of the equation. So, if I once again show it on a scale here, say this is the pipe, these are the two axes, this is the center line, this is T naught, right. So, T naught is obviously a constant, right, has to be a constant, right. So, what it implies is that your Tm starts to do this. This is the profile and this is of course your x, right. So, this is actually your Tm, right. So, Tm, T naught minus Tm is basically coming down, right. Okay. Now, if you look at that, what was the expression for Q double prime, that is the heat flux, it was H into T naught minus Tm at any x, right. So, naturally what it means is that Q is given by this particular difference between the two temperatures, right. So, what should be the nature of Q? Q should also come down in an exponential fashion, right. So, in other words, this comes down like this, correct. So, there is a decay of heat transfer rate, right, okay, and there is a decay in T naught minus Tm, right. Okay. So, basically what happens is that the mean temperature increases till it kind of approaches the wall temperature. Of course, it is never quite true because it is an exponential relationship. So, it never quite becomes equal, but the difference slowly and steadily goes down with x. That is what you can see from this particular expression, because it is an exponential term involving x, right. So, as x increases, this term should come down compared to what was the initial value. So, initial value is this one, say. So, let us say this one you can call it as T naught minus Tm at x1, right. It slowly comes down from that particular value, right, at the initial condition, from the initial conditions. So, that is an interesting thing. Okay. So, compare this to the constant heat flux case, whereas we saw that T naught and Tm both were increasing, but the slopes were the same, right. So, their difference was always the same. That is bound to happen because your Q double prime happens to be the same, it happens to be a constant, right. So, compare this to your constant heat flux case, if you recall, right. So, that was your Tm, T naught and Tm, right. There was this constant difference always that was maintained. That is because of the reason that Q double prime was a constant, and both of them increased in a constant fashion, right. Both of them increased in they were like parallel lines essentially, because their slopes were the same, right, and actually the slopes were a constant. That is why we got the linear variation, right. So, here of course, the variation of Tm is necessarily exponential in nature. Okay. It is exponential in nature, it increases exponentially. Okay. Now, based on this, okay, so let us look at the full expression now. Okay. If we have to do this, so u by alpha dt by dx right. That is essentially the expression that we have. That is the energy equation. We have done it plenty number of times. So, T naught minus T by T naught minus Tm, recall your definition of the fully developed temperature, right. It is G R by R naught. Remember, the Nusselt number is still a constant. If you recall, though the modes, the equations how we cast it is very different, but Nusselt number is still a constant. There is no that Nusselt number limit that we got through the scaling argument, that Nusselt number should be of the order 1, right, and it will be a constant, that is still valid here. Okay. So, whatever we found about this T naught minus T divided by T naught minus Tm equal to G as a function of R only, that is still holds, that still holds over here, right. So, T equal to T naught minus Tm into G R by R naught, or dt by dx or this is G R bar right. That is the expression that you get. Now, what is the standard thing? To use this particular expression back here, right, in the first term of the series, right. So, the first term obviously is going to be u is given by the hydrodynamically fully developed profile. So, the energy equation becomes okay. Okay. Now, also we know dTm by dx is given by 2 by R naught Q rho Cp into U, that is also given, that is a standard expression regardless of whatever. So, 2 by R naught into H T naught minus Tm divided by rho Cpu, correct. Okay. And H, if you recall, is nothing but Nusselt number, has to be a constant from our scaling argument, because that part we know that it has to be a constant, has to be of the order 1. So, using all these expressions now, let us substitute it back in the energy equation. So, the energy equation becomes 2u alpha or cast it in terms of Nusselt number. Okay. So, that is what you will get. Now, of course, to solve this equation you need the boundary conditions. So, the boundary conditions will be dg by dr bar is equal to 0 at r bar equal to 0, right, okay, at r bar is equal to 0, and g is equal to 0 at r bar equal to 1. Okay. Why g should be equal to 0 at r bar equal to 1? Because what is the definition of g? G is given by T naught minus T divided by T naught minus Tm. Okay. So, at r bar equal to 1, that means at the wall, what will be the value of temperature? It will be the same as the wall temperature. So, naturally this will approach 1, or this will be equal to 1 at r bar equal to 1, right. And similarly, the temperature profile will have a general inflection, so that dg by dr at r equal to 0 will be equal to 0, right. So, these two boundary conditions are fine. At the same time, one more boundary condition, one more thing that we have to be consistent over here is that there is a Nusselt number that is involved in this expression, right. To solve for this Nusselt number, you have to have a physical and meaningful definition of Nusselt number, right. You cannot have an arbitrary solution with any arbitrary value of Nusselt number. So, Nusselt number by definition is given by 2g r bar at r bar equal to 1, right. That is the generalized definition of Nusselt number, right. So, whatever we do, this particular constraint has to be satisfied, right, is to be satisfied. That means, whatever is the profile for that G, it has to obey that Nusselt number definition. That means, the Nusselt number has to be equal to this. This particular definition has to be obeyed, right. Now, there is no way of solving this equation in a normal way. So, you can do numerical schemes and other things. Okay. So, if you solve for all those things, your Nusselt number value will come out to be 3.66. 3.66 will be the value of your Nusselt number if you do all the manipulations that I showed over here. Okay. So, this actually shows that the Nusselt number for the uniform wall temperature is actually a little lower than the uniform heat flux. So, Nusselt number T naught equal to constant condition is about 3.66. Nusselt number for Q double prime equal to constant, right, that is about 4.36. Both are of the order 1, okay. Both are constant, which agrees with whatever we did say earlier, okay. But this one is slightly greater than this, slightly, right, greater than this, okay. So, you can see that the equations are also kind of very similar, right, that we got. The Nusselt number definitions are similar, the definition of G is very similar, the definition of Tm is similar. So, everything else is similar, except that we have applied, we have basically applied, okay, a new boundary condition and a little bit of a different way to cast the problem to get to this particular figure, right. Okay. Now, in table 3.2 of Bejan, okay, you will have a lot of for different cross section pipes. So, we have done it for circular cross section, say for example, square, hexagon, octagon, okay, these kind of cross sections. You can get an expression for the Nusselt number both for the fully developed regime, okay, and for the uniform heat flux condition as well as for the isothermal wall temperature, that means the constant wall temperature boundary conditions. In all of those cases, you will observe that the Nusselt number value for the uniform heat flux within a particular family is always higher than the corresponding isothermal wall temperature, right. Okay. So, that is what you will see always for all the cases, okay. And for fully developed flow for the circle shows the largest value of Nusselt number, right. Whereas, the same thing is valid for the isothermal wall also. For any other cross section, you actually have a reduction in Nusselt number, okay. So, that is what, so closer, for example, square will show a very low value of Nusselt number. Low means in a relative parlance, it will show a low value, but as you increase go to more and more higher order polygons, that means say hexagon, octagon and all these things, okay. That means you are closely approaching a circle. As you increase the number of sides of the polygon, you basically approach a circle, right. You slowly approach the Nusselt number limit of 4.36 for a uniform heat flux and 3.66 for a uniform wall temperature, right. But 3.2 and 3.3 of Bejan, okay, actually reports, and I will provide this as a supplementary material. It is actually all these Nusselt number values are compiled, okay. So, you will not show the details at how they were calculated, but the procedure will be essentially the same as laid down here. Of course, square and other things will be more 3D in nature, okay. So, it is a little bit more complex than what you can comprehend, but nevertheless, heuristically speaking, circle shows the largest value of Nusselt number, okay, followed by the higher order polygons. That means, in decreasing order of polygons, you have a decreasing order of your Nusselt number, okay. So, in the next class, we will start doing the things on what we call the isothermal. If the If the tube is surrounded by an isothermal fluid, then what happens? Thank you. Last class we did about uniform wall temperature. Now in this particular class, okay, we are going to start a little bit of a more complex problem which has got elements of both uniform wall and uniform wall temperature and uniform heat flux. This is basically a tube surrounded by isothermal fluid. So, situation is something like this. This is once again the tube with R and X. The wall temperature of the tube is T0, which is not specified. The temperature of the external fluid, right, is specified. So, this is the temperature of the external fluid that is given as constant. Now, imagine this to be a situation in which a tube is placed in some kind of a heat transfer fluid. So, it is typical heat exchanger type of a problem. There is an external fluid which through external convection is actually taking away the temperature. So, there is a hot fluid going inside the tube. Okay, that hot fluid is transferring heat to an external fluid which is outside the tube, right. Right now in the previous classes we are only concerned that there is a uniform heat flux or a uniform wall temperature. We are not concerned what happens outside the tube, right. We always thought that the wall temperature was kept constant by some means, or there was a uniform heat flux that was supplied along the tube wall. Okay, this is more realistic in nature, that this particular tube which is carrying some hot fluid is placed inside a large convective medium of some other external fluid, whatever that external fluid is. Can be the same fluid, can be a different fluid also, right. So, it becomes a typical heat exchanger kind of a problem. Okay. So, it is neither a constant wall temperature, neither it is a constant heat flux condition, right. However, the external bath is so huge, right, it is like a reservoir, large reservoir, that T infinity of the external fluid is kept constant. So, that means the external fluid is not varying in temperature, understood. So, it is like a large ocean. So, it is what we call typically a thermal reservoir, right, that temperature is not changing because T infinity value is very large, I mean the thermal inertia is very large, but however the wall and whatever is the wall temperature and the heat flux at the wall on the tube is therefore varying, okay, because that we cannot assume to be constant. Okay. So, similarly, so here Q double prime is given by some kind of a HE, some external convection coefficient, right. So, it is T infinity minus T naught, right, T infinity minus T naught, okay, where T naught obviously will be a function of x in this particular case, right, okay, and neither is Q double prime is a constant in this particular case. So, let us assume a few things, that the flow is fully developed. That has nothing to do with anything, right, the flow is fully developed. That means x is greater than the max of xt and xh, you know what xt and xh are, right. Okay. So, we are defining Nusselt number, define Nusselt number. This is a little bit of a strange definition of Nusselt number, T infinity minus Tm into d by k, right. What is T infinity? T infinity is the external fluid temperature, right. Tm is the mean temperature of the flow inside the pipe, right. So, this definition of Nusselt number is very different, because previously you had T naught minus Tm, right, or you had it in terms of the Q double prime, right. This is very different, that is because our Q double prime is defined in a very different way also, right. So, therefore, let us take T is equal to T infinity minus Tm into G r bar, okay. So, this is the definition that we are putting forward, okay, and this is the expression that we are casting, that T, that is the temperature, is as a function of T infinity and Tm, and it is this total expression is a function of R only. Okay, like in our fully developed regime, these are the things that we did. In addition, we say that the tube wall thickness is negligible. So that means this avoids the complication that there will be a drop inside the wall. Okay, got it. And therefore, its thermal resistance is also weak. So there is no thermal resistance of the wall. Okay, a wall is negligible. Okay, it's just because if it's a thick wall, you have to also take into account the thick wall effect. Okay, so we are discounting all that. Also, your dTm by dx is given by 2 R naught q double prime rho Cpu. This is the average axial velocity, right? This is the average axial velocity. Once again, this definition is once again the same as what we had earlier, right? That whatever we had in our previous class. Now, let us cast this problem. That means we first write the energy equation. Once again, I make it a habit that you write the energy equation, even though this has been written countless number of times, just that you guys get a feel, okay, of writing the same equation again and again. So once again, this is the same flow field, right, because U is accurately solvable. Okay, so therefore, you get this. Okay, or right. Okay, okay, just by using our own definition. Okay, now individually d square T by dr square is given as T infinity minus Tm G double prime R bar 1 minus G naught R naught square. Similarly, the first derivative and R is obviously R naught into R bar. These few things are given, right, given as a so I have not done anything funny over here except my definition of temperature and my definition of Q double prime. I have tweaked them according to the problem. That means I have involved the external temperature field into the picture, because that is the one that is constant, right, and the Nusselt number definition has changed a little bit. Okay, so based on that, I have started working on this particular problem. Okay, so in other words, if you cancel a few terms, then you will get G double prime bar right. We need several boundary conditions. So G prime bar is equal to 0 at R bar is equal to 0. Why that will be the case? Let us revisit the situation that what was our definition of G. That means your T was equal to T infinity minus Tm, okay, into Gr, right. Okay, so why Gr will be, or G prime R will be equal to 0 at R equal to 0, that is given by the axisymmetry of the temperature profile, right. So this boundary condition you can easily make out, okay. But what about the other boundary condition? Because at the wall you don't have a boundary condition properly now, right, because of your definition, because you have T infinity now. You cannot say when R bar is equal to 1, you will have g going to some value. Okay, you cannot say that. Okay, so let us recast it in a certain way. Define something called a Biot number. Okay, He R naught by k, right? He is the external heat transfer coefficient, right? He R naught by k. So that's a perfectly valid definition of the Biot number, right? Okay, so Bi into G bar is given as T infinity minus T divided by T infinity minus T infinity mean. Okay, got it? So similarly, Biot number at G R bar at R bar equal to 1, right? That is given as He R naught by k, okay, T infinity minus T naught divided by T infinity minus Tm. Okay, okay. So that is what we have. Similarly, at R bar equal to 1, k dt by dr at R equal to R naught is exactly given as He T infinity minus T naught, right? Okay, that is nothing but your Q double prime, right? That is also equal to your Nusselt number T infinity minus Tm into k by 2 R naught, right? So if I now do a little bit of manipulations on this, okay, or right, okay, which is nothing but if you are not okay, R bar is equal to 1, right. So you got your definitions, right, of that what will be your G prime at R bar equal to 1. Okay, you also got the definition of what is going to be your G bar, right. By introducing this basic definition of Biot number, this is Biot number, right, by using this basic definition of Biot number in this particular case. Okay. So now let us define something else also. Let us make it a little interesting. Let us define Nusselt number prime, something called a Nusselt number prime, which is basically Q double prime T naught minus Tm into d by k. This is basically what we call the duct side Nusselt number, right, because this uses the conventional definition of T naught minus Tm. This is the definition that you are most familiar with, right. Recall that your Nusselt number is basically T infinity minus Tm into d by k, correct. Okay. So therefore 2 by Nusselt number is equal to 2 T infinity by Tm divided by Q double prime k by 2 R naught. 2 by Nusselt number prime is basically 2 T naught minus Tm divided by Q double prime k by 2 R naught, right, right. Okay. On the other hand, your Biot number, 1 over Biot number is basically k by He into R naught, which is basically k by R naught T naught minus T infinity by Q double prime, right, or in other words, okay, 2 by Nu prime plus 2 by Nu. You just add the two together, right, it will come out as k R naught Q double prime T naught minus Tm minus T infinity plus Tm, right, or in other words it will come out to be minus k R naught into Q double prime T naught minus T infinity, which is nothing but 1 over the Biot number, okay, which is nothing but 1 over the Biot number. Got it? Okay. So, in other words, what we can write over here is that 2 by Nusselt number prime plus 2 by Nusselt number is basically equal to 1 over Biot number in this case. Got it? Okay. So, the final equation that needs to be solved in all these things is basically minus 2 Nusselt number 1 minus r bar square in G r bar is no different than the expressions that we had earlier, right, okay, with subject to the boundary conditions G bar at r bar equal to 0 is equal to 0, G bar at r bar equal to 1 is equal to Nusselt number by 2. Okay, two particular definitions we have. Now, solve this problem. This basically is an eigenvalue problem. So, solve this eigenvalue problem. Numerically, okay, numerically to get the answer. Now, there are two limiting conditions that are strictly possible for this particular case, right. Okay. So, what are those limiting conditions? Okay. So, let us before we spend a lot of time discussing it, let us look at that if your Biot number is basically, let us write down the most common definition of Biot number, this is this, right. So, in the limit that Biot number goes to infinity, right, Biot number goes to infinity, okay, that would imply, this would lead to that T naught must be equal to T infinity, right. Okay. So, this basically means that T naught is equal to constant, right. So, in this particular case the Nusselt number nu prime, right, which is the basically the duct side Nusselt number, that value should be equal to 3.66 in the limit that Biot number approaches infinity, right. Let us take the condition when Biot number approaches 0, right, which implies that He R naught by K is much less than 1, correct. Okay. So, this also implies very poor, okay, thermal contact, right. So, in other words, T naught minus T m in that particular case is locally independent of x, right. It's locally independent of x, and T naught minus T m is locally independent of x corresponds to a uniform heat flux case, right, because if you recall in your uniform heat flux you had these lines which were parallel, this difference was always constant regardless of x, at any x the difference will be the same. So, when they are locally independent of x, okay, that means when Biot number is much less than 1, okay, it is controlled by heat flux, or in other words this becomes a uniform heat flux case. That means the Nusselt number at Biot number approaching 0, right, will approach the, this is Nusselt number prime basically, Nusselt number of Q double prime equal to constant, right, that means it will be equal to 4.36. So, that will be the value of Nusselt number that you are going to get when once you have this kind of a mediation. Understood? So, we can see that these are the two limiting conditions, and in between you will have any value. These are the two bounds, right. 4.36 is one bound and 3.66 is the other bound, right, 0 and a very high number, right. So, in between all other Nusselt number values will be packed in between. So, we can see that when we actually did the uniform heat flux and the uniform temperature, we basically covered these two extreme ends. The actual situation is like a pipe in an isothermal fluid, right. So, that in between Nusselt number, whatever may be your configuration, will lie somewhere in between, right. So, that is an important case to note over here, right. Okay. Okay. Points to note, okay, in here. Okay. So, He, what we said over here is the external conductance. Do not confuse it with H. Okay. H is basically the internal conductance. Got it? This is a simple error that you try to make, that is internal and external, right. Okay. So, external conductance and internal conductance are very important. Just keep that thing in mind, because sometimes things might get a little jumbled up. Okay. Some general points to note is that the existence of fully developed T profile, okay, does not require assumption of large Peckley number. Note it down properly. It does not require the definition that the Peckley number has to be very large, right. Okay. Okay. But however, so this is one of the key assumption. It does not require the assumption that of the large Peckley number. However, Nusselt number equal to constant do come from that large Peckley number assumption. Okay. It do come from that large Peckley number assumption. Okay. So, based on this, okay, let us we can also draw a couple of profiles over here. Say for example, in the case of high Biot number case. So, this is your T infinity. Look at it carefully. This is almost like what your T wall looks like, right, and your T mean kind of curls up in this particular way. So, this is when the Biot number, okay, is approaches infinity, or in other words He is much greater than K over R naught, right. That means the external conductance is very high, right. That is what you would have. That means there is no gradient between the external fluid, in the external fluid, because if you recall, if you recall your example that when you said that you have this typical problem like a sphere immersed suddenly in a large thermal reservoir, what we say that when we do not have to take the thermal gradient within the sphere, we tell that when Biot number is much less than 1. This is the opposite to that, that if Biot number is very high, that means there is no thermal gradient on the surface of the sphere with the external fluid, right. It is almost like that heat transfer is like kind of instantaneous, but there will be substantial gradient that will be created inside the sphere, right. So, that is essentially, if you look at it, this essentially means that there is no real temperature gradient between T infinity and T naught, both are basically the same in a way, but therefore, there is a high temperature gradient within the fluid, which basically corresponds to the uniform wall temperature case. Okay. Similarly, you have the other situation, this is T infinity. So, this is actually your T naught, this is actually your Tm. They are, so here He is less than K over R naught. So, whatever happens in the external fluid, we do not really care, okay, because our internal conductance is very high, right. So, it is always controlled, it is not controlled by X, it is basically controlled by the heat flux, and that is exactly what we have drawn over here. Okay. So, that is I think the two grand definition. Okay. And if you look at any other fluid flow, you can refer to figure 3.12 of Bejan, convective heat transfer. There you will find that one would give you the flow, that means the Nusselt number variation with Biot number. Here we have drawn the two extremes cases. There they will show you for a Poiseuille flow, which is basically the flow that we are most concerned with. Okay. For that kind of a flow, that what will be the value of your Nusselt number, right. So, figure 3.12 of Bejan can be looked at. Looked for Nusselt number values for any, or here it is Nusselt number prime for any Biot number. Remember Bejan, in the Bejan's book, that the Nusselt number is cast in a different way. Okay, so you should, once you do it, you should keep in mind that what is the actual definition of Nusselt number, right? How he has defined it and how we have defined it as a part of this particular course, right. So, in other words, Bejan's figure 3.12 should be looked at very, very carefully, right. Okay. So, and we will also share that particular figure with you in the next class. Okay, we will start it there, and we will also show you the Nusselt numbers with for the different configurations. That means the cross sections. Those are mainly for handbook purpose. Okay. Because actual solving of this equation requires a little bit of effort, right, but you can still take a quick look. But all we can say that it varies from 0.436 to 3.66. So, that is the variation, that is the limit of variation of your actual Nusselt number, that is the duct side Nusselt number. It will always remain within these two bounds. Okay. So, that is but also you would like to pose a question that why is the Nusselt number for uniform heat flux higher, consistently higher for any cross sections as we saw, than the corresponding Nusselt number for a uniform wall temperature. Why is that the case? This is an open question that we are throwing open in this particular class, and we will give the answer a little later. But the students can start to think about that why is that the case, why this is consistently higher. And we saw all other Nusselt numbers seems to stack up in between these two limits, that is 4.36 and 3.66. So, what is the reasoning behind it, okay, if there is any reasoning, that is. So, I think spend some time looking into this. In the next class we are going to start looking at heat transfer to developing flow. So far we have looked at heat transfer in the fully developed regime, and we have also looked at the hydrodynamically fully developed, and we know what are the situations that are possible. Let us look at the developing flow regime and try to see what we can extract out of that. Many of the equations are basically not solvable in their full not solvable in a class, but you can always try, you can have numerical methods, you can have other sophisticated mathematical techniques by which you can solve it. Okay, but this is just to give you an essence that what is the key physics, okay, behind these kind of flow configurations. Okay. As discussed in the last class, we decided that we will show that how the Nusselt number and the friction factor for laminar flow, okay, with regular polygonal cross sections should vary. So, this is what you have. So, there are two limits, one is uniform heat flux, one is the isothermal wall. As we can see, for the fully developed flow, okay, so forget about the slug flow portion, we are going to come to that a little later. For the fully developed flow, as you can see, for uniform heat flux and for isothermal wall, these are the corresponding values of the Nusselt number, moving from square to circle. Okay. So, as you can see, as we increase the number of sides, that means we move closer to a circle. Circle is almost like an infinite polygon, right. So, as we move closer to a circle, as you can see, the Nusselt number increases, that is the heat transfer coefficient also increases for both isothermal wall as well as for uniform heat flux case. Okay. So, from 3.6 all the way up to 4.3 we move, and here from 2.98 all the way up to 3.66. Okay. This two, as we did the math and we showed that 3.66 and 4.364 were the two limits. Okay. Similarly, you can also look at the friction factor, which is basically comes from the hydrodynamics. Okay. There also, as you can see, that the friction factor actually increases a little bit, okay, as we move towards from a square to a circle. Okay. So, that is one. And if you recall, in the last class we said that when you actually have a cylinder placed in an isothermal reservoir, right, with T infinity was equal to constant, if you recall. Okay. So, we did that and we kind of showed that for that particular thing there are two limits which exist, if you recall, Biot number approaching infinity, Biot number approaching 0, right. and we said that those two number values lies between 4.36 and 3.66, right. So, this graph effectively shows that particular thing, all right. So, this is basically what we call the duct side Nusselt number. Okay. Recall this graph is taken from Bejan. So, the nomenclature is a little different. What Bejan uses as nu prime, I have used it as nu. So, there is a little bit of what we call a little bit of ambiguity, okay, between these two, okay, the Nusselt number. But the Nusselt number, this nu is basically the duct side Nusselt number. In this particular graph, I have used nu prime, okay, and I have used instead of nu hat what they have used, I have used nu in my derivation. So, just be a little careful when you actually look at and read the graphs. Okay. So, as you can see here very clearly it goes from 4.36 to 3.66, and you should look only into the Poiseuille flow profile, not the slug. Okay. What is slug will come a little later, but as of now this particular graph you can see that these are the two limits, okay, for a wide variety of Biot number. This is the Biot number that we have. As you can see, Biot number 100 is very high, that is it mimics the Biot number approaching infinity, and 0.1 is actually a low enough Biot number. So, you can take that to be the Biot number to be equal to a very low value. Okay. So, based on these two things you have these two limits that we have established in the last class, where we have shown that this is the way the Nusselt number, the duct side Nusselt number should vary. Okay. This is of course the external Nusselt number, okay, which was based on a nu that we wrote in our previous lectures. So, that varies in this particular way, okay, as you can see from this particular graph. Okay. So, this basically completes our discussion, the pending discussions that we had. Okay, and we have now given graphically as well as in the form of a table that how these constants will vary, what will be the nature of these profiles, and remember all these equations were basically solved in a numerical fashion. Okay. So, now we will go back to our thermally developing flow and try to understand that how thermally developing flow actually varies. So, you go to that particular part. So, let us look at the heat transfer in developing flow. That is what our main aim was. Okay. So, heat transfer in developing flow, we would come to the point that where you basically are dealing with a situation that in the entrance region, how does the heat transfer happen. So far we have dealt with the fully developed limit. We have established how the temperature varies, fully developed temperature profile varies as a function of R only, right, that we established. Okay. That means a normalized temperature profile. We also saw that what is a hydrodynamically fully developed region, how does it look like, but let us now look at the thermally developing part so that we can get an idea that how that is going to vary. Okay. So, there are situations, can be two situations. This is very similar to what we saw in our flat plate boundary layer, that how the two boundary layers are actually developing. This is delta T. So, this is once again x, this is once again x T, right. So, in this particular case your delta T is less than your delta, corresponds to Prandtl number much greater than 1 slot. This is like delta T is greater than delta, okay, and Prandtl number is therefore much less than 1. These are the two limits that we are very familiar with, right, and we already know that what Prandtl number greater than 1 means. Okay, that means of course that your thermal diffusivity is larger, right. Okay. So, that is how you are going to carry this. Okay. So, greater than 1, less than 1. Okay. So, let us take the limit of Prandtl number much less than 1, okay, which means that the delta t is actually greater than delta. Okay. So, this is the condition. Note that the definition of Prandtl number is gamma by alpha, right. So, when we say that this is much less than 1, this essentially means that alpha is much greater than gamma, right. So, in essentially what it means is the thermal diffusivity is more than the momentum diffusivity. So, in this case, by the definition of Prandtl number, this is what we have. So, delta t is much greater than delta. Okay. So, like your flat plate, okay, like your flat plate, delta t is proportional to x, Prandtl number to the power of minus half, Reynolds number x to the power of minus half. Okay. So, that is from the flat plate analogy that we already did, okay, for delta t which is greater than delta. Do you remember? So, you can just flip your notes and you can go to that particular page. So, at the end of developing length, at the end of the developing length you have delta t proportional to x t, Prandtl number to the power of minus half, Reynolds number x t to the power of minus half, right. Okay. So, at the end of the developing length, so that is what x t is at the end of that particular segment, right. Now, delta t is obviously at that particular point is nothing but the hydraulic diameter, right, of the duct, right. So, this is the hydraulic diameter, okay, is the hydraulic diameter. Therefore, we get dH is proportional to x t, Prandtl number to the power of minus half, Reynolds number x t to the power of minus half, right. Okay. Or in other words, dH is proportional to x t. Remember, this Reynolds number is cast in the terms of the length scale, which is x, not with respect to d. Okay. Or in other words, dH by x t, Prandtl number to the power of half into u x t by u x t by gamma is of the order 1, right, should be of the order 1, roughly scales as 1, right. Or in other words, if you now convert this particular Reynolds number to the corresponding diameter, I mean use that as the relevant length scale. So, x t by dH into 1 over Prandtl number write it properly, Prandtl number, Reynolds number d, right, to the power of half is proportional to 1, right. So, that is what you have over here. Okay. So, for this situation, so that is, this is very important because we will use this length scale very shortly. Okay. In how we will use it, we will see. Okay. Now, okay. If you now also look at this thing in a little bit more detail, this is the generic expression once again. So, x by delta t into Prandtl number to the power of minus half, Reynolds number x to the power of half is proportional to 1, or x by dH, dH by delta t, Prandtl number to the power of minus half, Reynolds number x to the power of minus half, this entire thing scales as 1, or x by dH to 1 over Prandtl number, Reynolds number dH to the power of half, dH by delta t is proportional to 1. Okay. So, as dt approaches dH, this particular ratio approaches 1. Okay. So, this particular ratio approaches, in the limiting case it is 1, as this approaches your dH, right. So, basically x by dH into 1 over Prandtl number REDH, okay, to the power of half, okay, is equal to 1. This is the one that governs, right, transition from developing to fully developed, right. This is the transition, this is the number, right. As it approaches 1, the flow becomes more and more fully developed. So, that is what we have got. Otherwise, normally your dH will be more than your delta t, right. So, this particular number, okay, has to be less than, if this is much greater than 1, this has to be less than 1 for the ratio to be equal to 1, right. So, therefore, as this approaches 1, okay, the flow becomes more and more fully developed. So, we are going to the fully developed regime, which is based on this particular criteria, right. So, that is an important part that one should understand, right. Next, we look at the case of Prandtl number greater than 1, right. We did it for Prandtl number less than 1. Okay. Now, here one important thing that we might want to do, if you recall your flat plate boundary layer, we did a scaling. Remember that we did something like this to establish the velocity scale. This is what we did, okay, for u, for scale of u. Okay. However, the basic assumption in that particular case was that delta t is much greater than or delta is much greater than delta t, right. That was the assumption in a flat plate boundary layer. Okay. So, therefore, this scaling was valid, but here it basically spreads over the whole diameter of the pipe. So, therefore, this scaling is not correct over here. The scale of u is still capital U, okay, that is still the scale, okay, because there is no there was no imposed scale, right. So, and the layer of delta t was much thinner compared to the delta. So, therefore, you could get away with this kind of a scaling. Now, so therefore, in this particular case also you apply the same thing, which makes it or x by dH right. So, that is what you this is what you got earlier, okay, from your hydrodynamics. Okay. This is from the flat plate. Instead of writing or, let us put also, okay, over here. So, therefore, x by xt is 1 over Prandtl number, or xt by x is equal to Prandtl number for all Prandtl number now, right, because your scale has not changed. So, there is no difference, okay, got it. So, therefore, for x less than xt, Nusselt number is given by d k q double prime into delta k into dH by k that is the Nusselt number value, right. So, in this developing region, got it. So, remember two things. One is that this is that for all Prandtl number. This is different from a flat plate where we had that Prandtl number 1/3 and half kind of a discrepancy, right. Here actually that does not exist, and also the Nusselt number definition is given by this. Okay. So, these two are two important points that you should always remember. Okay. Now, this sets the stage now to do a detailed analysis of the thermally developing flow, which is basically the Poiseuille flow. So, we would take that the hydrodynamics is fully developed, that means the flow is hydrodynamically fully developed, but it is still thermally developing, right. Okay. So, that is the case that we are going to take over here. So, thermally developing developing but hydrodynamically fully developed. Okay. So, as you can see, the first thing is your x lies in between these two limits. That means, x is greater than the hydrodynamic entrance length, right, but it is lower than x t, which is the thermal boundary length. Beckley number is much greater than 1, and Prandtl number is much greater than 1, right. So, these are the things that we have kind of put over here. T naught, which is the wall temperature, is equal to constant, and of course, you have dt by dr is equal to 0, still at r equal to 0 because of the symmetry, and we put a temperature T in, which is basically the inlet temperature for x greater less than xh. Okay. Okay. So, you can fix the origin whatever. Okay. So, you can fix the origin at x equal to xh. In that case, this will be less than 0. Okay. So, it depends on where you are fixing the whole thing, right. So, this looks like this. Okay. So, basically your hydrodynamic boundary layer has fully developed here. Is delta. So, this is your basically your coordinate, this is your region of interest, so to say, and this is T naught is equal to constant. Okay. So, this is your T naught equal to constant, this part, okay, and this is your hydrodynamically fully developed regime. Got it. So, based on this, okay, let us start define G, okay, is equal to T minus T naught divided by T in minus T naught, right. T in is the inlet temperature, right. R bar is equal to R by R naught. This you are already familiar with. For x bar, that is for non-dimensional, if you have to non-dimensionalize x, then it is x by d divided by RED into Prandtl number. Remember, this scaling now becomes important, which we established just a few minutes ago, right. So, this comes essentially from your scaling argument, and this scaling argument evolved very naturally, right, because we know that when this was equal to 1, we got to the hydrodynamically fully developed, to the thermally fully developed regime, right. That was what we actually did, right. So, if we recall all the assumptions that we had over here, what does the assumptions actually say? That first and foremost you are within. So, if this is basically your xt somewhere there. So, we are only interested in this intermediate region, because beyond this we have already done our analysis, okay, for constant wall temperature and constant heat flux, right. So, here we are taking the case of wall temperature is still constant. So, we are not varying that. The profile of temperature, by intuition you can say that it actually should have an inflection point at r equal to 0, that is at the center line, and the inlet temperature is taken to be the inlet, okay, whatever is the inlet temperature, okay, but we are considering our axis starts basically from your x equal to h, right. So, the inlet temperature actually is x less than 0, to say. And there are 3 parameters we are defining. One is G, which is basically nothing but a non-dimensional temperature. It is different from how we defined it earlier. Now, you have a T in coming into the picture. Previously, we did not have that. Then of course, you have the R bar, and this particular term is very important, which one could only establish through the scaling argument that we did earlier. So, this is just a brief recap or a brief emphasis on what needs to be done to approach the problem. So, next is the energy equation, obviously. Okay. So, energy equation right, that is the full fledged energy equation. Of course, you still have the Peclet number much greater than 1 limit. Okay. So, u is basically 2u into 1 minus r bar square, t equal to t naught plus g, t in minus t naught, r is equal to r naught into r bar, x is basically equal to d red Prandtl number x bar, right. So, these are the parameters which we are going to substitute now in the expression and try to see what does the math, how does the math actually evolve, right. Okay, so let's take term by term, that is easier for us to do, because that would give us that flexibility, and then we can assemble all the terms together. So, dt by dx is equal to dg by dx t in minus t naught, which is basically equal to dg by dx bar t in minus t naught divided by d Reynolds number d into Prandtl number, right. So, we have just used the scale for x in this particular expression. So, then you of course is dt by dr, and that is given as dg by dr t in minus t naught dg by dr bar t in minus t naught into 1 by r naught. Okay. So, that is the second term that you get. Similarly, dt square by dr square. So, we are writing term by term, as we said, 1 by r naught square t in minus t naught d square g by d r bar square, right. That is what we have done. So, these are the three terms. Now, the basic task is to basically assemble all these terms together so that we can get a nice expression. So, 2u 1 minus r bar square by alpha t n minus t naught by d into red into Prandtl number and dg by dx bar, right. That is the first term. 1 over r naught square t in minus t naught d square g by d r bar square plus 1 over r naught square 1 over r bar t in minus t naught and dg by dr bar, right. This is the full fledged expression assembling all the terms. So, this is basically assembling all terms, right. Okay. So, therefore, moving on, or so a little bit more mathematical manipulations. Okay, or in other words, half plus 1 by r bar dg by dr bar, right. So, that is the final form of the expression that you have. Okay. As you can see, there are two variables, almost impossible to solve because g is no longer a function of only r. Okay. It is a function of both x and r, right. So, the boundary conditions are g equal to 0 at r bar equal to 1, which is given, right. dg by dr bar is equal to 0 at r bar equal to 0, this is symmetry, okay, and g is equal to 1 at x bar is equal to 0, right, because that is the point where we have the same temperature, the temperature is the same as the inlet temperature, right. So, based on these expressions, so to say, okay, we move forward, got it. Okay. So, this equation actually presents, it can be only solved, we will try to solve it analytically. So, there are methodologies by which you can actually solve it analytically. So, one of those methodologies will be the separation of variable or SOV. Okay. So, separation of variables. You can read up a little bit on separation of variables in your math from your math book. Okay. So, separation of variables is something that you have encountered quite a bit in your conduction courses, because many of the conduction equations actually has that kind of a thing. Okay. Now, if you look at the nature of this equation once, so you can see one thing very prominently. Okay. If you just look at this term, okay, I mean this term and these two are basically the same. So, these two terms, right. You can see that it is now a function of two variables, where your x bar kind of is like a time, okay, whereas r is more like the spatial distance. Okay. So, so we will see while we are doing this. Okay. So, what is our expectation? Our expectation is that the temperature would show a certain amount of behavior, certain kind of behavior with x bar, right, because as x bar increases, okay, something is going to happen to the temperature profile, right. That is what is expected is going to happen. Now, what is the general expectation? See, when we actually propose that what is going to be your g, let us write the g here one more time so that you guys get an idea. T by T naught into T in minus T naught. So, what happens to g as we go on increasing x bar? Does g skyrocket or it does not, right? So, obviously, t is something that is bounded. Okay, it cannot go beyond a certain value, it cannot go beyond T naught, right. So, based on that, okay, whatever is the solution that we will get out of solving this equation has to be physically meaningful also. That means you cannot have a temperature profile which skyrockets, which increases all the time. Similarly, you cannot have a temperature profile which cannot have a temperature profile which shows an unphysical nature, right, even if it is mathematically correct, right. So, based on some of those limitations that we have, we are going to do the separation of variable, keeping in mind that this is our main variable, which is g, which is a function of both r and x, right. So, separation of variables we are going to attempt in the next class, and we are going to see that how this separation of variable actually works and what it actually leads to, what are the expressions that we get ultimately out of it. Thank you.